There is an element in the periodic table that behaves like a spy. It disguises itself as lead. It looks like tin, but it has properties that break the most basic rules of physics. We used it for hundreds of years without knowing its real name. We treated royalty and common soldiers with it. We cast it into the letters that spread the Reformation across Europe. And we hid it inside the mechanisms that guard your sleep, in fire sprinklers bolted to the ceiling above your head right now. But here is the part that changes everything. For as long as modern science existed, this element was classified as eternal, the last bastion of nuclear stability, the heaviest element whose atoms would never decay. Textbooks printed it, professors taught it, students memorized it. 20 years ago, a team in France proved it was a lie. This element is not eternal, it is dying. Its agony just lasts longer than the universe itself has existed. Element number 83, bismuth. And today, we are taking it apart, atom by atom. Before we can understand what bismuth is, we need to understand where it came from. And the answer is violent. On August 17, 2017, gravitational wave detectors in Louisiana, Washington State, and Italy simultaneously recorded a signal, a ripple in the fabric of space-time itself. The source was 130 million light-years away. Two neutron stars, the ultra-dense remnants of two separate supernova explosions, had been spiraling toward each other for billions of years. On that day, they collided. The collision lasted seconds, but telescopes recorded a flash that burned for days. And the spectra of that flash showed something extraordinary. Heavy elements were being forged in the debris: gold, platinum, and bismuth, in quantities that dwarfed anything a single supernova could produce. By the calculations of astrophysicists, those few seconds of collision created more gold, platinum, and bismuth combined than the entire mass of the Earth. This was the missing piece. For decades, physicists had known that heavy elements form inside stars through nuclear fusion. But fusion has a ceiling. It stops at iron. Every fusion reaction up to iron releases energy. The star burns fuel and shines. Past iron, the equation flips. Fusion starts consuming energy instead of producing it. The star cannot sustain itself. It collapses. And in the catastrophic seconds of that collapse, a flood of neutrons tears outward, slamming into lighter nuclei, building heavier ones at a speed so ferocious that the nuclei cannot decay between captures. Physicists call this the R process. It builds gold, uranium, bismuth in moments. But when they added up all the supernovae in the history of the observable universe, the numbers did not balance. There was too much gold, too much platinum, too much bismuth. The universe had more heavy elements than dying stars alone could explain. The neutron-star collision of 2017 was the answer. A second forge, rarer but far more productive. Two stellar corpses spiraling in darkness for billions of years, producing in their moment of impact what no other process in the cosmos could match. That material scattered. It mixed with interstellar clouds. 4.5 billion years ago, when our solar system condensed from one of those clouds, bismuth was already here. It had been waiting. Now the history. And this is where the detective story begins. Bismuth does not hide alone. In the Earth's crust, it concentrates alongside tin, lead, copper, and silver. Wherever miners dug for those metals, bismuth came along. And for centuries, nobody could tell it apart. It looked silvery, with a faint pink or cream tint. It was heavy, like lead. It behaved in some reactions like tin, in others like antimony. The confusion was total. This was not stupidity. This was the absence of tools. Before modern analytical chemistry, identifying a new element required guesswork, tradition, and luck. Bismuth had none of the dramatic properties that would force recognition. It did not glow like phosphorus. It did not explode like potassium. It did not stink like sulfur. It sat quietly in the ore and let everyone assume it was something else. By the 10th century, miners in the Erzgebirge, the ore mountains on the border of modern Germany and the Czech Republic, were working with this metal regularly. They called it Weiße Bergmetall, white mountain metal. They dug it from the same silver mines that funded European commerce for centuries. The cities of Annaberg, Joachimsthal, and Freiburg were the centers of this trade, and bismuth passed through all of them, unnamed and unrecognized. The first serious written record came in 1546. Georg Agricola, a German scholar who was also a practicing physician and city councillor in Joachimsthal, published a treatise on mining and metallurgy. His masterwork, De Re Metallica, appeared in 1556 after his death. 12 books, hundreds of woodcut illustrations, descriptions of every known metal and the technologies used to extract them. In it, bismuth is described as a distinct metal, different from lead and tin, with its own properties and its own behavior in the smelter. Agricola saw it with his own eyes. He worked among the miners. His descriptions carried the weight of direct observation. But recognizing bismuth as separate from lead did not make it an element. That step took another 200 years, because chemistry as a science did not yet exist. What existed was alchemy, and alchemists saw bismuth as something intermediate, not quite lead, not quite tin, not quite silver. Some called it immature lead that had not yet transformed into silver under the influence of subterranean juices. Others classified it as a variety of antimony. The confusion persisted. While the chemists argued over classification, the practitioners were already putting bismuth to work, and the first large-scale use was on human faces. In 15th and 16th century Europe, a white face was the mark of aristocracy, health, and purity. To achieve this effect, women and men of the court used ceruse, a mixture of lead carbonate and vinegar known since ancient Greece. It produced a brilliant white finish. It was also catastrophically poisonous. Lead penetrated the skin, accumulated in the body, destroyed the nervous system. Users lost teeth, suffered neurological damage, and did not understand that the cause was their cosmetics. Queen Elizabeth I of England reportedly applied ceruse in layers several millimeters thick, literally a mask of poison. This was considered normal. Bismuth offered a similar effect with far less toxicity. Bismuth oxide and bismuth subnitrate gave a stable white finish to skin. This was the first relatively safe decorative cosmetic in European history. Not safe by modern standards, but a genuine improvement over lead. By the 15th century standards, it was progress. Simultaneously, bismuth entered another industry that would change the world: printing. In the 1440s, Johannes Gutenberg invented movable metal type and the printing press in Mainz. To cast individual letters, he needed a metal with specific properties. It had to melt at a low temperature for easy casting. It had to fill the mold precisely for sharp relief. It had to be hard enough to withstand thousands of impressions under the pressure of the press. And critically, it could not shrink on cooling, because shrinkage meant the letter came out smaller than the mold, losing definition. Most metals shrink when they solidify. Bismuth expands. This made it an essential component of typographic alloy. The standard composition was tin, lead, antimony, and bismuth in proportions adjusted by trial and error over decades. But bismuth was always present. The books that spread the Reformation, including the works of Martin Luther, whose printing runs in the 16th century, numbered in the hundreds of thousands. The Bibles in vernacular languages, the works of Copernicus, Galileo, Vesalius, all printed bismuth in the type. Element 83 played its part in the dissemination of knowledge, invisibly, in every cast letter. In 1753, a French chemist named Claude Geoffroy the Younger ran systematic experiments that finally settled the classification question. He measured bismuth's density, its melting point, its behavior in acids. The differences from lead were unmistakable. Bismuth was its own substance. 1753 is often cited as the year of bismuth's scientific discovery, though miners had been handling it for 2 centuries before that. Then came Lavoisier, 1789. His elementary treatise on chemistry, the first modern chemistry textbook, introduced the concept of a chemical element as a simple substance that cannot be broken down further. Bismuth made the list. From that moment, it was official. Element 83 had a name, a number, and a place in the system. though the periodic table itself would not arrive for another 80 years. Now the properties. Because bismuth is an anomaly, it breaks rules in at least 5 places, and every one of those violations turned out to be useful. First, the weight. Bismuth's density is 9.78 grams per cubic centimeter, heavier than iron at 7.8, lighter than lead at 11.3. But unlike those metals, bismuth is brittle. Hit it with a hammer and it shatters like a mineral. Its crystal structure does not allow atoms to slide past each other under stress. This is the opposite of what you expect from a heavy metal. Second, the melting point, 271.5 degrees Celsius. For a metal, this is remarkably low. Zinc melts at 420, copper at 1085, iron at 1538. Bismuth sits near the bottom, alongside tin and lead. This property opens the door to alloys with astonishingly low melting points. Wood's metal, a classic example, is 50% bismuth, roughly 27% lead, 13% tin, and 10% cadmium. Its melting point is 70 degrees Celsius, below the boiling point of water. A spoon made from this alloy will melt in a cup of hot tea. Looks like a magic trick, explained by phase diagrams. And these alloys are not toys. They are in the fire sprinklers above your head. Each sprinkler head is sealed with a fusible alloy or a glass ampule that breaks at a precise temperature. When the air reaches 68 or 93 degrees, the alloy melts, the seal breaks, and water flows. Bismuth is what lets the temperature be tuned precisely, and bismuth does not corrode or change its properties over decades. Install it and forget it. Third, expansion on solidification. Almost every substance shrinks when it freezes. Atoms settle into tighter arrangements, but bismuth does the opposite. Its crystal lattice occupies more space than the liquid melt. Among metals, only bismuth and gallium share this property. Among common substances, water does the same, which is why ice floats. This anomaly made bismuth indispensable in early printing. When Gutenberg and his successors cast movable type, they needed a metal that would fill the mold precisely and not shrink on cooling. Ordinary metals left the letters slightly smaller than the form, losing sharpness. Bismuth expanded. The letters came out crisp. The Bibles, the pamphlets, the scientific treatises, the works of Luther and Copernicus and Galileo, all printed with type that contained bismuth in the alloy. Element 83 played its part in the spread of knowledge, invisibly, in every cast letter. Fourth, electrical conductivity. Bismuth is a metal, but a terrible conductor. Its electrical conductivity is 30 times lower than copper, 7 times lower than lead. This seems like a defect. It turned out to be a superpower. When conductivity is low, any change in it becomes far more visible. Magnetoresistance, the change in electrical resistance under a magnetic field, is dramatically more pronounced in bismuth than in good conductors. Lord Kelvin used bismuth for his systematic studies of magnetoresistance in 1856, precisely because the effect was cleanest on this metal. Edwin Hall discovered the Hall effect in 1879, again using bismuth, because the voltage signal was strongest here. The Hall effect is now in every smartphone, every car engine controller, every industrial sensor, billions of devices per year. And the physics was first mapped on the worst conductor in the lab. Fifth, diamagnetism. Most people know that magnets attract iron. That is ferromagnetism. But there are materials that magnets repel. They are called diamagnets. And among all metals, bismuth is the strongest diamagnet. Place a piece of bismuth between the poles of a powerful magnet, and it pushes itself away from the field. With superconducting magnets producing fields of 10 Tesla or more, a small bismuth sample can be made to levitate, suspended in midair by nothing but the opposition of induced magnetic fields. The physics behind it is the lens effect. An external field induces tiny currents in bismuth's electrons, and those currents generate their own field, pointed against the external one. In most metals, this effect is negligible. In bismuth, it dominates. Now the discovery that shattered an axiom of chemistry. For as long as the periodic table existed, bismuth held a specific title, Element 83 was the heaviest stable element. Beyond it lay polonium, astatine, radon, francium, radium, all radioactive. Everything past bismuth decays. But bismuth itself, according to every textbook, every reference table, every nuclear physics course, did not. It was the boundary, the last island of permanence. In 2003, a group of French physicists at the Institut d'Astrophysique Spatiale in Orsay set out to test that claim. They built a detector from bismuth germanate crystals and cooled it to 20 millikelvins, 20 thousandths of a degree above absolute zero. At that temperature, atomic vibrations nearly cease. The crystal becomes silent enough to hear the faintest energy signature. To understand what they were listening for, you need to understand alpha decay at the quantum level. The nucleus of bismuth-209 contains 83 protons and 126 neutrons. 126 is a magic number in nuclear physics, a neutron count that fills a complete shell and confers unusual stability. 82 protons would also be magic. An element with 82 protons and 126 neutrons is lead-208, the doubly magic nucleus, the terminus of 3 of the 4 natural decay chains. Everything heavier than lead has a thermodynamic incentive to shed mass and decay toward it. Bismuth, with exactly 1 proton more than lead, sits just past the line. Alpha decay requires the alpha particle, a helium-4 nucleus, to escape the nuclear potential well. Inside the nucleus, the strong force holds everything together. But the strong force is short range. Beyond a few femtometers, electromagnetic repulsion takes over. The alpha particle faces a barrier, the Coulomb barrier, a wall of repulsion it lacks the classical energy to climb. In classical physics, it stays trapped forever. But quantum mechanics does not operate by classical rules. Particles do not have exact positions. They exist as probability distributions, wave functions that extend into and through classically forbidden regions. There is a vanishingly small but non-zero probability that the alpha particle's wave function penetrates the barrier and materializes on the other side. This is quantum tunneling. For bismuth, the barrier is wide. The energy released is small, roughly 3.1 million electron volts, and the tunneling probability per unit time is so extraordinarily tiny that the resulting half-life stretches to 19 billion years. The Orsay team watched for weeks. They accumulated events, cataloged each by energy, timing, and position within the detector. They subtracted every source of background noise one by one. Cosmic rays striking the detector from above, natural radioactivity from the laboratory walls and floor and ceiling, trace contamination in the crystal itself, thermal fluctuations in the cryogenic system, electrical interference from nearby equipment. Layer by layer, source by source, they peeled away the noise. What remained was a population of events at exactly the energy expected from bismuth-209 alpha decay. The signal was faint. Statistically, out of the roughly 10 to the 22nd bismuth atoms in the crystal, perhaps a few dozen had decayed during the entire observation period. A few dozen events out of trillions of atoms. The result was published in Nature. Bismuth-209 emits an alpha particle and becomes thallium-205. The measured half-life, 1.9 times 10 to the 19th years, 19 billion years. The age of the universe is 13.8 billion years. Bismuth's half-life exceeds it by a factor of roughly 1.4 billion. In all the time the Earth has existed, 4.5 billion years, the fraction of bismuth atoms that have decayed is so small it has no practical meaning. Bismuth remains perfectly safe. It creates no measurable radiation, but formally it is radioactive. The practical consequences are zero, and this deserves emphasis. A standard dose of Pepto-Bismol contains on the order of 10 to the 22nd bismuth atoms. The number that decay during the hours the compound spends in your digestive tract is a statistical handful. Alpha particles cannot penetrate the dead outer layer of skin. You receive more radiation from the potassium-40 in a banana. Bismuth subsalicylate is safe. The pharmacists were right. Nothing practical changed on the day the Orsay paper was published, but something conceptual did. If bismuth is not stable, then no element above lead is stable. The line moved, and this opens a deeper question that physicists have been pursuing for decades. Are the protons themselves stable? The proton is a component of every atomic nucleus. If protons decay, then all matter, every metal, every mineral, every body, will eventually disintegrate. Over timescales that make bismuth's half-life look like a blink, but finite nonetheless. The standard model of particle physics predicts proton stability. But theories beyond the standard model, grand unified theories, allow proton decay with half-lives of 10 to the 34 years or more. The Japanese detector, Super Kamiokande, a vast chamber containing 50,000 tons of ultra-pure water ringed by 11,000 photomultipliers, buried inside a mountain in Gifu Prefecture, has been searching for proton decay since 1996. In decades of observation, not a single event has been confirmed. The lower limit on the proton half-life currently stands above 10 to the 34th years, but absence of observation is not proof of absence. It means only that if decay occurs, it occurs more slowly than our instruments can yet detect. If proton decay is real, then nothing in the universe is permanent. Not bismuth, not lead, not the atoms in your bones. The question is not whether, but when, and the timescales stretch so far beyond human comprehension that the word forever becomes not a fact, but a horizon we cannot see past. Now the pharmacy, because this is where bismuth meets most people, usually without them knowing. Pepto-Bismol, Dinol, Ulcavis. These are trade names for medications containing bismuth subsalicylate or bismuth subcitrate. They are prescribed for gastritis, stomach ulcers, and digestive disorders. The active ingredient is bismuth, and for centuries, nobody understood why it worked. They just knew it did. In 1982, an Australian physician named Barry Marshall and a pathologist named Robin Warren made a discovery that would earn them the Nobel Prize in Physiology or Medicine in 2005. They proved that most stomach ulcers are caused not by stress, not by spicy food, not by excess acidity, but by a bacterium, Helicobacter pylori, a microorganism living in the stomach lining, destroying its protective barrier. Before this discovery, ulcers were treated with antacids. Symptoms faded, the bacterium stayed. Months later, the ulcer returned. Millions of people lived with this cycle, believing ulcers were chronic and incurable. Marshall and Warren showed they were curable. Kill the bacterium and the ulcer heals. And bismuth kills Helicobacter pylori with remarkable efficiency. Bismuth ions disrupt the bacterium's enzymes, destroy its cell membrane, and block its attachment mechanism. For human cells, bismuth in therapeutic doses is essentially harmless. It absorbs poorly into the bloodstream, does not accumulate in tissues, and exits the body naturally. This means the apothecaries of the 15th century were accidentally treating a bacterial infection 300 years before germ theory existed. They gave bismuth for stomach complaints, and their patients improved. Pure empiricism, 3 centuries ahead of the explanation. Today, bismuth is part of the standard quadruple therapy protocol for Helicobacter pylori. A proton pump inhibitor, plus 2 antibiotics, plus a bismuth compound. 4 components. Effectiveness above 90% when followed correctly. This is the official recommendation of the World Health Organization. But the stomach was not the only place where bismuth served as medicine. There was another chapter, darker and more dramatic. Before penicillin entered clinical practice in the 1940s, syphilis was one of the most feared infectious diseases in the world. Untreatable, slowly progressive, devastating to the nervous system and internal organs. The first effective treatment appeared in 1909, salvarsan, an arsenic-based compound synthesized by Paul Ehrlich and Sahiro Hata. It worked, but arsenic is a poison, and the drug's toxicity was a serious problem. In 1921, French physicians Constantin and Levitate published results of clinical trials using bismuth injections to treat syphilis. The results were promising. Bismuth suppressed Treponema pallidum, the bacterium that causes syphilis, and was tolerated by patients far better than arsenic compounds. For the next 2 decades, until penicillin became widely available, bismuth preparations were the primary treatment for syphilis in many countries. Millions of patients. This is a page of medical history that is almost never mentioned today. Now the part that connects bismuth to superconductors, MRI machines, and fusion reactors. In 1986, Swiss physicists Georg Bednorz and Karl Müller, working at the IBM Research Center in Ruschlikon, discovered a new class of superconductors based on copper oxides. The transition temperature was dramatically higher than anything previously known. They received the Nobel Prize in Physics in 1987, less than a year after publication, one of the fastest Nobel Awards in history. In 1988, researchers synthesized a superconductor based on bismuth. Its full chemical name is bismuth strontium calcium copper oxide, abbreviated BSCCO and pronounced BISCO. Different phases of this material superconduct at temperatures between 20 and 110 kelvins. The 110 Kelvin phase corresponds to minus 163 degrees Celsius, still cold by everyday standards, but warm enough to be reached with liquid nitrogen, which is cheap and abundant. The critical achievement with BSCCO was practical. Most high-temperature superconductors are ceramics. They are brittle. You cannot draw them into wires. But BSCCO was successfully manufactured as flexible superconducting tape. Tape that bends without losing its superconducting properties. This tape is now used in the magnets of medical MRI machines, the ones that scan your internal organs without radiation. It is used in experimental tokamak fusion reactors, where plasma is confined by magnetic fields. It is used in prototype superconducting power cables that could transmit electricity with 0 losses. Bismuth in the MRI machine scanning your brain. In the fusion experiments meant to solve the energy crisis. In the power lines of the future. For a metal that medieval miners mistook for impure lead, the career trajectory has been extraordinary. Now the physics that points toward the future, because bismuth may have its most important role still ahead. In 2005, theoretical physicists Charles Kane and Eugene Mele at the University of Pennsylvania predicted a new class of quantum material. In 2008 and 2009, experimental groups at Stanford, Princeton, and Berkeley confirmed the prediction. The first experimentally verified 3-dimensional topological insulators were bismuth selenide and bismuth telluride. A topological insulator is a material whose interior does not conduct electricity, but whose surface does in a special way. Electrons on the surface move in directions determined by their quantum spin. They cannot scatter backward when they hit a defect in the crystal. Quantum rules forbid it. They simply flow around the obstacle and continue. This is potentially a perfect conductor of surface current, with no losses and no dissipation. Why bismuth? Because topological behavior emerges in materials with strong spin-orbit coupling, the interaction between an electron's spin and its orbital motion. Spin-orbit coupling increases with atomic mass. Bismuth, one of the heaviest non-radioactive elements, has exceptionally strong spin-orbit coupling. Its compounds are natural candidates. The implications reach toward quantum computing. Topological insulators can host a special type of quasi-particle called a Majorana fermion, a particle that is its own antiparticle. Majorana fermions, if harnessed, could form the basis of topological qubits, quantum bits that are inherently resistant to the errors that plague current quantum computers. Microsoft's Station Q program is investing heavily in this direction. An element known since the 15th century, dug from medieval mines in Saxony, may become the foundation of computers we have not yet learned to build. Now the part of this story that connects bismuth to the edge of the solar system. In 1834, French physicist Jean-Charles Peltier discovered that passing an electric current through the junction of 2 different conductors either releases or absorbs heat, depending on the direction of the current flow. The reverse also works. Heat one side of the junction and a voltage appears. Heat becomes electricity. This is the Seebeck effect, discovered 13 years earlier. Both effects are the basis of thermoelectric devices, and the best thermoelectric material at room temperature, better than anything else found in 2 centuries of searching, is bismuth telluride. Bismuth telluride conducts electrons well, but conducts heat poorly. This paradoxical combination is exactly what thermoelectrics demand. Phonons, the thermal vibrations of the crystal lattice, scatter strongly in its complex structure. Electrons pass through relatively freely. The result is a material that converts temperature differences into electrical current more efficiently than any competitor near ambient conditions. Every Peltier cooling module sold today, the ones in portable car refrigerators, in CPU coolers, in medical equipment that maintains precise sample temperatures, is made of bismuth telluride. No moving parts, no refrigerant. Apply current, one side gets cold, the other gets hot. Reverse the current, reverse the sides. And now space. Radioisotope thermoelectric generators, the power sources on interplanetary probes, convert heat from decaying plutonium-238 into electricity using thermoelectric elements. Voyager 1, launched in 1977, is now more than 20 billion kilometers from Earth, the most distant human-made object in history. It still operates. Its thermoelectric generators, built with silicon-germanium alloys, the technology of that era, still produce current. But modern RTG designs for future missions to the outer planets increasingly rely on bismuth telluride elements, which are more efficient at the lower temperature gradients these generators produce as their plutonium fuel ages. The next generation of probes, heading beyond the orbit of Neptune, will likely carry bismuth in their power systems. Element 83, riding into interstellar space. Now submarines. Because bismuth played a role in one of the Cold War's most classified programs, Soviet Project 705, NATO designation Alpha Class, was a series of nuclear-powered attack submarines built in the 1970s. 7 boats, crew of just 32, compared to 80 or more on comparable Western submarines. Titanium hull, and a reactor cooled, not by water, but by a liquid alloy of lead and bismuth. The eutectic, the specific ratio that gives the lowest melting point, liquefies at 123.5 degrees Celsius. This alloy transferred heat far more efficiently than pressurized water, allowing a compact, high-power reactor that gave the Alpha class a submerged speed of 41 knots. No Western submarine could keep up. American naval intelligence was alarmed. These boats moved faster than most torpedoes in NATO arsenals at the time. But the lead-bismuth coolant had a fatal weakness. It could never be allowed to solidify. If the reactor lost power for any reason and the coolant temperature dropped below 123 degrees, the alloy froze in the pipes. Remelting it aboard ship was nearly impossible. Several boats were crippled by exactly this failure. The Soviet Union never fully solved the problem. After the collapse, all Alpha-class submarines were decommissioned by 1990. The technology, however, did not die. Today, lead-bismuth fast reactors are considered one of the leading concepts for Generation 4 nuclear power. Russia's SVBR-100 project, the European Union's Alfred demonstrator reactor, and several American startups are all working with lead-bismuth coolant. The submarine technology of the 1970s is transforming into the civilian nuclear energy of the 2030s. Now cosmetics and pigments. Because bismuth has been on faces and on roads longer than most people realize, the cosmetics connection runs deeper than most realize. In the 16th century, bismuth compounds already served as the safer alternative to lead ceruse. But the modern story begins with bismuth oxychloride. This compound produces a distinctive pearlescent shimmer thanks to its layered crystal structure. When light enters the layers, it scatters and reflects the way mother-of-pearl does in a seashell, creating a soft, luminous, iridescent effect that synthetic glitter cannot replicate. This is why high-end cosmetics manufacturers prefer it. Eyeshadows, face powders, foundations, bronzers, lip gloss. If the ingredient list says bismuth oxychloride, the shimmer you see is not plastic particles. It is the optical physics of a crystalline layer structure. the same thin film interference that colors the Hopper crystals, applied at industrial scale to a face powder. The pigment story is equally striking. In the 1980s, industrial chemists developed bismuth vanadate as a bright yellow pigment. It was designed as a replacement for lead chromate and zinc chromate pigments, which contain hexavalent chromium, a known human carcinogen. Workers who manufactured chromate pigments faced elevated risks of lung cancer. The European Union's REACH regulation and similar frameworks globally began restricting chromate pigments. Bismuth vanadate stepped in. It produces a bright, saturated yellow that resists fading under ultraviolet light and remains stable at high temperatures. It does not leach toxic metals. It does not degrade. Today, bismuth vanadate colors industrial paints, automotive coatings, plastic housings, and printing inks. The yellow center line on highways, the yellow paint on school buses in some countries, the bright yellow on construction equipment and safety signage. In each case, the color you see is bismuth, an element that medieval miners discarded as worthless impurity now determines the color of the lines you follow home at night. In optical glass manufacturing, bismuth compounds produce glasses with high refractive indices. These specialized glasses are used in precision optics, camera lenses, microscope objectives, and medical endoscopy equipment, applications where ordinary glass cannot bend light sharply enough. And the economics are peculiar. Global bismuth production is roughly 20,000 tons per year, a negligible amount compared to steel at 1.9 billion tons, or aluminum at 65 million. Almost all bismuth is obtained as a byproduct of smelting lead, copper, and tin. It rides along in the ore, ends up in the slag, and gets extracted as a bonus. This means the supply of bismuth depends not on demand for bismuth, but on demand for lead and copper. If lead production falls, bismuth production falls with it, regardless of how much the market needs it. China controls roughly 80% of world production and reserves. The irony is structural. Bismuth is increasingly used as the environmentally clean replacement for lead, in solder, in hunting shot, in fishing weights. But its production depends on the very metal it is supposed to replace. Increase your demand for the substitute, and you still need the original to supply it. This is not a crisis today, but it is a vulnerability specialists in strategic materials are already documenting. Now the crystals, because this is the part you cannot describe with words alone. When you melt bismuth and let it cool slowly, something happens that looks designed. The crystals grow not as random lumps, but as geometric staircases. Each step is a precise right angle. Each level is slightly offset from the one below. The result is a miniature ziggurat, a structure that looks architectural, deliberate, impossible for something that just solidified from a pot of liquid metal. The explanation is the rhombohedral crystal lattice of bismuth, combined with its anomalous expansion. The edges of each growing crystal face radiate heat faster than the centers. The edges build up, the centers lag. Each new layer is smaller than the last and offset, creating the terraced spiral. Physics builds architecture without a blueprint. Then color. The moment the crystal contacts air, oxidation begins. A thin layer of bismuth oxide forms on each terrace. The thickness varies, a few tens to a few hundreds of nanometers, comparable to wavelengths of visible light. When light strikes this film, some wavelengths reflect from the top surface and some from the metal beneath. The two reflected beams interfere. For one color, the interference is constructive, and that color intensifies. For another, it is destructive, and that color vanishes. The result is a crystal that shimmers through the entire rainbow, deep blue to violet to gold to green to red and back to blue. Every crystal is unique. No two are identical. You can grow them at home. Bismuth pellets are available online. Melt them in a steel pot on a kitchen stove. Let the melt cool. When a solid skin forms on the surface, tilt the pot and pour off the remaining liquid. The crystals clinging to the walls and bottom will be Hopper crystals. Let them oxidize in air and watch the terraces bloom into color, 20 minutes from start to finish. The most beautiful object chemistry produces, from a pot on your stove. This month, We followed elements through the hidden architecture of the world. Lithium calmed the human mind before it powered a phone. Fluorine burned everything it touched until we caged it. Arsenic killed for 5 centuries until one chemist taught the world to detect it. Cobalt connected a child in Congo to a battery in Connecticut. Uranium turned out to be the most precise clock in nature. Tungsten refused to break. Phosphorus built DNA and bone, and now we are mining the finite rock that supplies it, faster than the planet can replace it. Bismuth did none of those dramatic things. It sat on the periodic table for 2 centuries wearing a label that said stable, filed under harmless, growing crystals that look like staircases to nowhere, hiding in your medicine cabinet and in the ceiling above your head. And all that time, at a rate so slow that the entire observable history of the cosmos amounts to a rounding error in its half-life, it was falling apart. One alpha particle at a time, one quantum tunneling event at a time. Too slowly for generations of physicists to detect. An atom of bismuth that exists right now in a fire sprinkler above your head, or in a tablet of stomach medicine in your bathroom, or in the yellow road marking you drove over this morning, that atom is older than the sun. It formed in the collision of neutron stars before our solar system existed. It survived every mass extinction in Earth's history, every ice age, the entire journey from the first bacteria to the species that learned to measure its half-life. It will outlast the sun, which will become a red giant in roughly 5 billion years and consume the inner planets. In those 5 billion years, a negligible fraction of bismuth atoms will have decayed, on the order of 0.001%. The atom will drift through interstellar space. It may enter the next generation of stars and planets. It may settle on the floor of a new ocean. It may be found by beings we cannot conceive of. But if proton decay is real, if the universe is built so that all matter eventually dissolves, then even this atom will one day vanish. Not in a billion years, not in a trillion, in timescales that make 19 billion years look like a heartbeat. Stability is not a fact. It is a measurement we have not yet been precise enough to disprove. Everything decays. The question has never been whether. The question is whether you are patient enough to notice. Next month, we go deeper, into the elements you cannot see, cannot touch, and cannot escape. Start with the one that might be in your basement right now, seeping through the concrete, colorless and odorless. That is where we begin.